The discovery by the ancient Greeks that certain lengths in geometry were incommensurable with other lengths does not seem to have bothered anyone very much for the next 2 millennia. After all, irrational numbers are irrelevant for practical purposes. This is because whenever a physical measurement is made, the result is given as a rational approximation to whatever degree of precision is needed. But sometime after the invention of the calculus in the 17th century, mathematicians began to be concerned with obtaining clear understandings of such things as limits and continuity and of the nature of the number line itself. At that time, irrational numbers had been understood in much the same way as the ancient Greeks had understood them, that is, in a way that was very much tied to the geometrical idea of incommensurable lengths. And so it was that by the mid-19th century, some mathematicians were seeing a need to separate the real numbers from the old geometrical ideas and to understand them in terms of number only. To conceive of the counting numbers and the rational numbers without thinking geometrically was not really a problem. But finding a way to define the irrational numbers in this way had seemed more difficult. However, the German mathematician Julius Wilhelm Richard Dedekind thought of a way to do it. Dedekind observed that any point on the number line cuts it into 2 non-overlapping parts. His idea was to translate this observation into the realm of pure numbers by making something like a cut in the set of rational numbers. The rational numbers could be partitioned into 2 subsets. Dedekind reasoned that the rational numbers corresponding to points to the left of the point in question on the number line would be put into one subset, and all the other rational numbers, those corresponding to the remaining points on the number line, would be put into the other subset. There is an underlying assumption here, which we take to be an axiom, that there is a natural correspondence between points on the geometrical number line and the set of pure numbers. Now, every rational number would be in one or the other subset. If the point of interest on the number line was a rational point, it would correspond to a rational number, and this number would be in the upper of the 2 subsets. However, if the point in question was not a rational point on the number line, it would correspond to no number in either subset. In fact, in this case, the cut between the upper and lower subsets of rationals corresponds uniquely with the irrational point on the number line. Thus, such a partition of the set of rationals defines an irrational number. In the first part of this talk, I indicated that in this part there would be an easier proof of the irrationality of root 2. Many such proofs have been devised, and each is worth studying for the method and insight it contains. The following proof may seem straightforward, but it rests on a hidden assumption that really needs to be recognised. Instead of proving that root 2 is irrational, we may as well prove that root n is irrational for any positive integer n that is not a square. Suppose root n, for some such n is rational, then we can write root n equals a over b, where a and b are integers without any common factors. Now this means n equals a squared over b squared, but a squared and b squared are again integers without common factors, so n cannot be an integer, contrary to assumption. The contradiction shows that root n cannot be rational if n is a non-square integer. Now where was the hidden assumption? What if it had been possible to factorise a squared and b squared differently from the way a and b could be factorised? Then it may have been possible to cancel common factors from the fraction a squared over b squared so that it turned out to be an integer after all. However, this can't happen according to the fundamental theorem of arithmetic, which says factorisation of integers into primes is essentially unique. Now we come back to mid-19th century Germany. In the 1870s, Dedekind's friend and colleague Georg Cantor made some remarkable discoveries about the real numbers. Among other things, Cantor showed that most numbers are irrational. Cantor made his discoveries by considering infinite sets. He realised that some, but not all, infinite sets could be lined up against the counting numbers 1, 2, 3, and so on. The set of even numbers is of this type, so is the set of square numbers, and perhaps surprisingly, so is the set of rational numbers. Any set that can, in principle, be presented as a list can be matched against the counting numbers and is said to be countable. The rational numbers can be listed by grouping them systematically according to the sums of their numerators and denominators. There will be many repeated numbers in the list, but these can be passed over when counting them off. Cantor then showed that the set of real numbers was of a different kind. He proved that no interval of the real numbers could be presented as a list, and so the real numbers were not countable. Suppose, on the contrary, that a way has been found to list all the numbers between, say, 0 and 1. We can make sure each of them is written uniquely as a non-terminating decimal by making the terminating decimals end with an infinite string of 9s rather than zeros. We imagine all the numbers in the interval written down in an infinitely long list. The very clever step that Cantor took was to show that he could always construct a new number that was not in the supposedly complete list. Here's how. Make the first digit in the new number different from the first digit of the first number in the list. Now make the second digit in the new number different from the second digit of the second number in the list. Continue in this way, making the nth digit in the new number different from the nth digit of the nth number in the list. Thus, the new number is different from every number in the list in at least one decimal place. A contradiction has been reached. The original list could not have been complete after all, and so the numbers in the interval from 0 to 1 must be uncountable. Clearly, there are a great many numbers that are not in the countable set of rational numbers. In this sense, the uncountable set of real numbers is a larger set than the countable set of rational numbers. We have already identified some irrational numbers, the square roots of non-square integers greater than 1. To these we could add the cube roots of non-cubes, and similarly the nth roots of integers greater than 1 that are not nth powers. Numbers of this type are called algebraic numbers because each of them is a root of some polynomial equation with rational coefficients. It turns out that even this infinity of irrational numbers is still countable, because the set of polynomials of which they are the roots is countable. there must be still more irrational numbers that are not of the algebraic type. Thus, Cantor's argument showed that non-algebraic irrational numbers exist without actually displaying any of them. This class of irrational numbers is called the transcendental numbers.